So I want to wish everybody good morning or good afternoon, depending on which part of the world you're in. And welcome to the second lecture of this Neutrons in Soft Matter Science series. Um, I will try to carry on from where I left off last time. I just wanted to say in passing that for those of you who have questions, um, you can ask them anytime via the chat box, and I will look at it. I'll keep looking at it and try to reply when you ask those questions. Um, Also, I will probably try and have a 5-minute break in the middle of the lecture for you to ask questions if you want to, and then we'll go on, and then you can also ask questions at the end. But feel free to ask questions if there's something that is urgent, even during the lecture. Okay? All right. So I want to say a couple of things that I didn't say last time. One is that because of the penetrating power of neutrons, um, one advantage is that you can actually study systems under working conditions in actual cells, like catalytic cells or electrolytic cells or batteries or whatever, or chemical reaction cells. So because they penetrate and they penetrate through windows, and they're not concerned about gases or anything in the material. So that, um, to some extent, shared by X-rays, is one big advantage of these kinds of probes. So here I am showing you a diagram which is similar to the diagram for the wave vector transfer that I showed you last time. Here I'm assuming that the scattering is elastic, so that the incident wave vector, which is actually going this way, is equal in magnitude to the outgoing wave vector, and the typical angle of scattering is 2 theta. Half of that angle, if you got Bragg scattering, as you will probably realize, those of you who've taken crystallography courses, half of that angle is called the Bragg angle, and the relationship between Q in this case and theta is that Q is twice from, you can see from this trigonometry from this triangle here, that Q is 2 k naught sine theta, or 4 pi over lambda sine theta, where theta is half the scattering angle, and this is always true for elastic scattering. However, let me just say that a couple of remarks about elastic scattering. We're assuming here that in many of the things that we're studying, the scattering is elastic, like small angle scattering. It's certainly true for diffraction, reflectivity, diffuse scattering, and so on. This is not necessarily completely true, and you notice that I've been utilizing the expression for d sigma by d omega, or S of q, which assumes no energy analysis of the outgoing beam. Now, for X-rays, this doesn't matter. Even if there's some small energy transfers, the q is essentially the same, because it's a tiny fraction of the wave vector. But for neutrons, if there's significant inelastic scattering, and of course we're seeing everything that comes off, then there have to be corrections, because your Q will also be shifted when the scattering is inelastic. And the corrections for this are well known, and they're called Placzek corrections. But we're not going to go into those complications here. We're going to assume that for our purposes, the scattering is essentially elastic for small angle scattering reflectivity. When we talk about inelastic scattering specifically, then we'll talk about energy changes. But for the moment, let us just assume that K outgoing and K incoming have the same magnitude. So having said that, let me just say, I say here at the bottom, that in the kinematic approximation that I've talked about here, where I've derived S of q or d sigma d omega, you notice that basically it depends only on the wave vector q. So actually, in this approximation, which is a pretty good approximation for most scattering, um, the scattering that we are interested in is a function only of Q. And it doesn't matter whether you're using one energy, incident energy. It's independent of the incident energy, whether you're doing it with time of flight or with a crystal diffractometer. The one thing that matters is the wave vector transfer Q. Now, of course, if you're doing so S of Q is independent it's the basic function we're trying to get at. Now, if you can measure it with under different conditions, if you use very high energy neutrons, for instance, then these angles here become rather small for the same Q, and your spectrum becomes inconveniently bunched up near the forward direction, and that may not be desirable. But you can allow for those effects. And in fact, for many, as we shall see, for many applications involving small angle scattering, reflectivity, and so on, in the case of neutrons, it is convenient to work with rather large wavelength neutrons, typically of the order of sources have cold sources to produce sufficient fluxes of cold neutrons, these large wavelength neutrons, for our experiments. Okay, so let's go on. This is to remind you again of the thing that we measure. This is basically the scattering function S of Q for an amorphous system. Or actually, in this case, it's liquid argon. I showed this last time. And here's the pair distribution function, corresponding pair distribution function. This can be measured at any length scale. This is a liquid, so the length scales here are atomic. But of course, you can also study nanoparticles and their pair distribution functions at much larger length scales, in which case you'll be working essentially in the small angle regime. And but the formalism is independent of that. And one thing I wanted to mention is that this first peak in the structure factor S of Q, or any peak that appears in these kinds of scattering S of Q measurements, usually indicates sort of neighbors at a distance which is at 2 pi over the value of this value of Q. So remember, when you see scattering with neutrons, or even X-rays actually, in S of Q, where there's a peak in the scattering from some disordered or amorphous system, it just means that there are preferentially neighbors at a distance of 2 pi over that Q away from each other. All right, we'll come back to that later. Now I want to talk about small angle scattering, which is small angle neutron scattering. The same thing applies to small angle X-ray scattering, of course. Now, the length scales that we probe in a scattering experiment are essentially at any wave vector Q, essentially the length scale is 2 pi over Q. And so what that means is that basically when you study rather large length scales, you want to work at small q. There's an inverse relationship between q and length, and you can see that by the fact that q is actually measured in inverse nanometers and length is measured in nanometers. So this means that if you want to study rather large lengths, rather large objects, macromolecules, spacings between large nanoparticles or spacings between them, you want to do your experiments at a rather small q. So you want to do your experiments, you want to do basically small angle scattering. And so that's why this small angle scattering is done on instruments where you normally employ rather large wavelengths of neutrons, and you go very far away from the sample, typically with an area detector, so you get sufficient resolution in Q, so you can go down to rather small Q values, and you collect the data in the pixels. And the details will be discussed I'm sure, in the lectures by Dr. Hamilton and others on small angle scattering later on. So I'm just trying to give you the formalism here. Now, the point is that if you're looking at small q or doing a small angle experiment, you're essentially looking at rather large length scales, which smears out the atomic structure. So you're not sensitive to the interatomic spacing. And so usually you can assume that, suppose you're looking at some nanoparticle or some protein in solution or a polymer, you can normally assume that you neglect the atomic structure and you assume that what you're looking at is kind of a blob and you're interested in its size and its shape. And that blob, you can assume to a good approximation, has a constant scattering length density. I want to introduce you to the concept of scattering length density, which is the scattering length times the number of nuclei with that scattering length per unit volume, and you average this over all the kinds of nuclei there are. So if there are different nuclei with different scattering lengths, you weight them by their volume fraction, and you construct what's called the scattering length density, and that essentially controls the contrast for small angle scattering experiments. Now, so let us assume that we've got some kind of object which has a certain volume and shape and a certain scattering length density, and there's just one such object. So we're assuming a very dilute solution for small angle scattering, and it's floating in a solvent in solution, and we want to consider the scattering from this object. Well, as we know, the intensity for, as I showed you, the intensity for scattering at any wave vector q is essentially the double Fourier transform of the density at r times the density at r prime. If there's only one object, we can forget about correlations, and then this thing can just be written as the Fourier transform of the density modulus squared, basically, this double Fourier transform. And in this case here, the rho of r is the coherent, the scattering length density. I should emphasize that we're only talking here about weighting with the coherent scattering length times the density of that kind of nucleus, not the incoherent. And for X-rays, it's just the electron density. So that's what it is, and that's the expression for this, essentially for what you see if you've just got essentially one object in solution here for simplicity. And that's true in the dilute case. Now, of course, if you considered the average scattering to be constant, then you know that the Fourier transform of a constant is a delta function in Q. And so the scattering from something that has only a constant scattering length density or uniform liquid is only in the forward direction. There's no small angle scattering from that as per se. And so we ignore that and we consider only the deviation from the average scattering length density. That's what gives you the small angle scattering. So we call that delta rho. That's the deviation of the object's scattering length density from the average scattering length density in solution, and that's the contrast. So when you write that as a modulus squared, you can see that basically, and since you assume that it's a constant scattering length density inside the particle, then you can see that, therefore, in this dilute limit, the scattering from a small particle is the scattering length density of the particle minus the average scattering length density of the solution. If there's only one particle, it's basically the scattering length density of the solvent, modulus squared, times essentially the modulus squared of this shape factor, which is just the integral over the volume of this particle, e to the minus iq dot r, and that is called the form factor because it represents the shape of the particle. And so all the information about the size and the shape, the volume and the shape, is contained in this quantity here. So we denote that by f of q, and so this is f of modulus q squared, and f of q is called the form factor. Sometimes the modulus squared of f of q is also called the form factor. It depends on the convention, so you should be careful when you're looking at lectures on small angle scattering or something as to what the definition is. But I'm defining f of q whose as the form factor, and its modulus squared is what goes into the intensity. This is defined in analogy to X-ray form factors where the Fourier transform of the electron density on an atom is the atomic form factor and is involved in the scattering. Those kinds of atomic form factors don't appear in neutron scattering because you're scattering essentially from the nucleus here, which is a point, and its form factor is a constant, so it's a delta function. So there's no question of an atomic form factor for neutrons, unless you're talking about magnetic scattering, where you're scattering from the magnetic electron cloud, in which case you do have to consider a magnetic form factor. But we're not going to go into that in this course. So let's go back to discussing what we mean here by the intensity function for one particle. If this, so let's consider this form factor here. It is the Fourier transform over the shape of this volume, and if that volume is a sphere of radius r, then this form factor is given by basically the Bessel function j naught, little j naught, and here's the volume of the particle as a prefactor. And by the way, there should be, as I've said here, in the original slide, I had to make a correction. There should be a factor of 3 here, and then it's sine q times the radius of the sphere, and it's this expression here. And when q goes to 0, this goes to the volume of the sphere. Sometimes the volume is taken out, and the form factor is defined as just the rest of the factor, which is defined to go to 1 as q goes to 0. Okay, so just be aware of that. Now let's continue with, so this is, we'll talk more about the scattering from a spherical particle in a moment, but let's consider now a couple of properties of this form factor. So if this is the form factor here, and let's just do an expansion in powers of q of this exponential, and then we can write this as a series, which is like this, basically the volume, then a term linear in q and involving r dr. But if you take the origin as the center of mass of that volume of that particle, this vanishes by definition, and then you're left with the next term, which is essentially the integral of q dot r squared, integrated over the volume of the particle, averaged in some sense, since we're taking this as a constant factor outside. Now you can see that q is in some arbitrary direction. The particle, we're averaging over all orientations of the particle. So q dot r is basically qr cosine theta. So there's a cosine squared theta that has to be averaged here over all directions. And you know that the integral of cosine squared theta in all directions in 3 dimensions is 1/3. So this gives you q squared, you can pull that out, over 6 times this integral. And this integral is nothing other than the second moment of the shape of the particle, basically r squared dr over the volume of the particle. And this, by the way, is a 3-dimensional integral, and this dr is meant to be a vector integral over the volume of the particle and not a scalar integral. So this quantity actually is, so when you modulus square this is a small correction to 1, so this becomes 1/3 because of the factor of 2. And then you can see that there's this term here, this equal sign should not be there. I've corrected that here. But you can see that the intensity goes like basically 1 minus 1/3 times q squared times this quantity here, which we can, the second moment, we call that the square of rg, which is defined as the radius of gyration of that object. Okay, and you can see that this is the same way moments of inertia are defined in mechanics. It's some measure basically of the size of the particle, and so it's a quantity that comes up quite often in polymers and discussing various objects. we call it RG here. So, so this is the small q expansion of the small angle scattering intensity. And you can see that you could almost, if you think of this as the leading terms of the expansion of an exponential, then you can see that you can sort of also approximate IQ by basically the contrast squared times the volume squared times some constant which involves the incident beam intensity and the resolution and so forth. And this exponential, this is just an approximation at small q, I should emphasize, because all of this expansion is only valid at small q. But you can look at this as being the leading expansion of e to the minus 1/3 q squared rg squared. And this is the famous Guinier approximation, which was put forward by Guinier, and is very useful in when you do a small angle scattering experiment to just get an estimate of the size of the particle. Because what you do is you do a log-log plot of the, you do a log intensity versus q squared plot, as I will show you, and the slope of that is negative 1/3 rg squared, and you extract the radius of gyration. So you can straight away tell from the small q scattering what the size of this particle is in the dilute limit. Having gone there, so now let's go into this in a little more detail. The scattering from spherical particles, as I've said before, is given basically by this quantity squared, and it's 3 times the volume of the sphere times sine QR minus QR cosine QR, and it tends to the volume here is defined as tending to the volume here as Q goes to 0, and it's a function that goes like this. It oscillates, and for elliptical particles, this is replaced by this expression, and this is the angle between the major axis, if it's an ellipsoidal particle, and Q. And then you have, if the ellipsoids are randomly oriented in the solution, pointing in all directions, you have to actually do a numerical integration over all possible directions of theta in 3 dimensions. Okay, so this is basically now sometimes also, of course, you don't have a particle. Even if you do have a set of dilute particles, they may not all be exactly the same size. So they may not be exactly what we call monodisperse. And so you have to take polydispersity into account in general by taking this form factor squared, weighting it with some probability distribution of radii within some range, and then integrating that over that range. And we'll discuss this in a minute. So, if you just have a dilute solution of spherical particles, this is basically what the scattering ideally would look like. It would be very sharp and going all the way down to 0 here, and then bouncing back up with many oscillations. If the particles were completely monodispersed. Now, actually, nature does produce almost spherical particles which are pretty monodispersed, almost exactly monodispersed, and those are things like viruses, right? And so if you do, there have been published small angle scattering from viruses, and they show these beautiful oscillations, which are not usually damped out very much. But in practice, these oscillations are damped and smeared out because you have polydispersity effects. The radius is not exactly constant. You have to integrate over radii. And of course, there's also instrumental resolution effects. So when you do those integrations in practice to analyze your data, you find that your ideal spherical form factor is slightly smeared out. I see there are no questions so far, so let me continue. You guys feel free to ask questions at any time, okay? So here I've given you some references. You can go on the web, and there are many things on the web with published form factors for all kinds of various objects: spheres, cylinders, ellipsoids, disks, I've listed some of them here. You can go on these websites. Bulem Hamuda has got a nice series of lectures on the web on small angle scattering, and he gives the derivation of some of these form factors in chapters 27 and 28. So I'm just putting them here for references if you want to look up form factor and you don't want to, you're too lazy to calculate it yourself. All right, now let's talk about an important thing in small angle scattering is this question of contrast. Okay, with X-rays you usually can't do much about contrast unless you tune towards the resonance of the X-rays or not. But with neutrons, there's a huge variation in the coherent scattering length for various kinds of nuclei and therefore of assemblies of nuclei. And the scattering length densities of various objects are shown in this diagram here. And you can see that they go all the way from H2O, which has a negative scattering length density, to D2O, which has a positive scattering length density. And then you have proteins and polymers and various things in between, which is nice because if you want to contrast match, okay, if you want to make some part of the object or some object disappear in the small angle scattering, all you have to do is put it in a solvent which is exactly contrast matched with that object. And you do this in general by choosing whatever the solvent is if you're using water, but it's also true for organic solvents, which you can deuterate. You calculate the appropriate mixture of H2O and D2O, and that will exactly contrast match some parts of the object or the object itself. And this is very convenient and one of the big advantages of neutron scattering. So, yes. No, it simply means that the wavelength that is scattered from a nucleus with a negative scattering length has a phase of, of pi relative to one with a positive scattering length. It's just a question of the phase. Okay? So the question was, what does a negative scattering length mean? And I was answering that by saying that a negative scattering length and a positive scattering length simply refer to the phase of +1 or -1 of the amplitude of the spherically scattered wavelength from that kind of nucleus. Okay. So here you can see that just an optical example. You've got a solution of Pyrex balls and fibers, Pyrex fibers, beads, glass beads and Pyrex fibers in solution. And here the solution exactly contrast matches out the Pyrex fibers, so you can only see the beads. But here the beads are contrast matched out and the fibers show up, so you can see this whole thing looks milky because it's full of fibers. So you can see how various parts of an object or various components of a sample can be made visible or invisible or separated in a small angle scattering experiment by choosing the right combination of solvents. Okay. And here is a list of the coherent scattering length, and which tells you that you can change the contrast by changing the scattering length for different isotopes. Here's hydrogen and deuterium. Here's tritium for completeness, but no one is suggesting that you use tritiated water in your, which is radioactive anyway, in your solvent for experiments. But H and D are important. And in certain cases, if you want to do experiments for typically hard condensed matter, oh, my audience has gone to sleep again, so we have to make some motion to get the light going. Whenever the lights go out, it means my audience has fallen asleep, and we need some light back. Okay, so here are various scattering lengths for different nickel isotopes, for example. So if you want to change the contrast, an expensive way to do this is to get different isotopes. But generally, H and D are good for most soft matter experiments, as you probably realize. Now, to go through some examples, here's a scattering from an isolated ideal Gaussian coil. So if you take a polymer uh, in an ideal solvent in solution, it can form something close to an ideal Gaussian random coil, and the form factor for that was worked out and is called the Debye function, and is listed here as this expression, which is often quite useful in analyzing polymer chain scattering. But of course, you may argue that you very rarely do experiments on a single isolated Gaussian coil in a solvent. If you have very dilute polymer solution, it's true you can approach that. If you want to do it with a concentrated solution, on the other hand, what you can do is you can selectively deuterate some of the chains, and they have a contrast, and they're sufficiently dilute that they give you a form factor which stands out above. So you can have, for instance, a polymer melt, which is the space is full of polymer chains, but if a few chains are deuterated, for instance, and the rest are not, or all the chains are deuterated and two or three are protonated, you can get the form factor of the chains in the melt from this method. An alternative method of getting form factors from a non-dilute case is to randomly deuterate some chains and not others, and then it looks like incoherent scattering. And the incoherent part of that scattering, which is related to the contrast between the deuterated chain and the non-deuterated chain squared, essentially gives you the form factor squared of the individual chains. So that technique is often also used if you don't want to go to very dilute solutions, but want to measure the conformation of a chain, but in a concentrated solution. You just do it with a randomly deuterated set of chains. The details will probably be covered in further later lectures. One thing I wanted to point out about this form factor is that it asymptotically goes like 1 over q squared. So whenever you see this asymptotic behavior 1 over q squared, that sometimes is an indication that you've got a nice Gaussian coil, scattering from a Gaussian chain or a polymer chain in solution. I'll talk about this in some more detail when I've talked about fractals. There's a question? Oh, thank you. How to know our sample's contrast? Then we could know the needed combination of the solvent. That's a good question. The only way you can estimate, it's true that you don't know your sample, you want to study it, but you can roughly say what your sample is made of, what its density is, and what the atoms it's made of are, and you could in principle try to calculate its scattering length density and therefore calculate its contrast. And for instance, if you're looking at silica particles, you know the scattering, you can calculate the scattering length density of silica because you know the scattering length of silicon and oxygen, and you know the densities. So in many cases, it's possible to calculate in advance or to estimate in advance the scattering length density, and then you can calculate what combination of H2O and D2O you need. But of course, in some cases, you don't know that, you don't quite know the sample, and then you have to do it by trial and error. And there are very interesting small angle experiments, actually, where you slightly change the mixture of H2O, D2O, and keep measuring the scattering until you get a nice minimum in the curve where the scattering actually is essentially, the contrast essentially goes to zero. And so you can contrast match by selectively and accurately deuterating partially your mixtures and doing this as a function of the concentration. It's a painful process, but it has been done several times, and it's often advised if you really want very carefully to get zero contrast for some part of your sample. Okay, so another question. How did they get the contrast matching beads image? That was an optical, that was just an optical photograph taken with ordinary light. So we're talking there about macroscopic objects. Okay. Um, you know, the optical contrast is as true for light as it is true for neutrons. So the same thing applies there. Okay, and now let's talk. So here's what I was talking about. If you plot the logarithm of intensity versus q squared, at small q, you often get a linear behavior, and that can be used to extract the radius of gyration. Therefore, the first is the easiest thing to just get roughly the size of the particle. Now, what are the various applications of small angle scattering? So you can see, you can study particles in dilute solution, polymers, micelles, colloids, proteins, precipitates. You can measure even in non-dilute case, you can measure the correlation between particles in concentrated solutions, aggregates, fractals, colloidal crystals, liquids, and you can measure two-component or multi-component systems like binary fluid mixtures, porous media, spinodal decomposition, and so on. All of these systems can be studied with small angle scattering. And also, if you've got systems of nanoparticles in solution, you can use small angle scattering, just measures S of Q, so you can use it to measure the PDF function, the pair distribution function. And if you've got a pair distribution function, often you can read off immediately what preferred distances there are between particles, or what the various bond lengths are. Now, if the particles are not dilute, you have to also consider the interaction, the correlations between particles, and so you actually have to consider the full S of Q, which, based on the previous formalism I gave you, can now be written as the sum over all pairs of particles in solution times the form factor of each particle times e to the iq dot RL minus RL prime, where these are the positions of the particles. Now, in general, this structure factor can be modeled, and of course, if the particles are fairly far apart, then this S of Q will produce peaks in the structure factor, the first peak being 2 pi over the average distance of the particles. If that average distance is very large, these peaks will be at very small q. Sometimes if it's dilute enough, there's such small q that they're actually inside the beam stop that you don't see around q equals 0 to prevent the area detector being damaged. You put a beam stop which cuts out the really small q regions, and so actually what you see then is just the asymptotic part, where S of q has essentially gone to 1, and you're measuring just the form factor, just as in the dilute limit. But if that doesn't happen, then you have to analyze the small angle scattering using both the structure factor, fitting both the structure factor and the form factor. And that's in the most general form of the scattering. And in general, you have to assume some model for the structure factor. And there are several models for random collections of hard spheres or various other types, or even things which have an attraction for each other. In liquids, they're the so-called Perkins-Yevik models and various other things like that. So these actually models exist. And as I say, models for your shape and size of the particle also exist, so you can fit the parameters in those models to the data and analyze the small angle scattering that way. So basically, that's what you measure. Now, there's one special case that I want to talk about, which probably not very familiar to you, and that is what happens if your particles or your object is a so-called fractal object. Now, a fractal object is a sort of interesting thing. It is in principle, mathematical fractals are defined as objects that can be scaled up or down, and they look exactly like the original object, right? So they're called self-similar. This can be true in a statistical sense for randomly aggregated particles, for instance, within certain length scales. From the size of the particle up to the size of the aggregate, you can have self-similarity in a statistical sense. But in any case, one of the defining properties of a fractal object is that the amount of material inside, or the density, the number of particles inside a radius r, is given by some power of r, which may not be an integer. Now, we're all used to solid objects where the number of particles in a uniform solid object goes like r cubed. And so for a uniform object, the fractal dimension is 3. For a sheet of paper or a smooth plane, d is 2, because the number of particles inside a radius r is proportional to the area, which goes like r squared. And for a rod, d is 1, because the number of particles inside a rod of radius r, inside a radius r, inside a very long rod, goes linearly with r. So these are commonly known objects where d is 1, 2, or 3 integer values. But the whole point about fractals is that you can have objects where d is non-integral or fractional and can be some number between 0 and 3 in some fractional value. And this is called the Hausdorff dimension, or the fractal dimension of that object, and is defined by this essentially the scaling law, that the number of particles inside a radius r goes like r to the power of d, where d may not even be an integer. This is responsible in many cases in small angle scattering, or in scattering from certain systems. You see this interesting power law behavior. S of q behaves like some power of q. And so if you plot S of q in a log-log plot, not this is log versus q squared, but if you plot S of q in a log-log plot, you often see over a certain range, a large range of q, you see linear behavior. And this power law often is evidence of this scaling behavior, as I will show now. For instance, let's consider, let's assume this is true, and then let's ask ourselves, from this we can derive how many particles are at a distance between r and r plus dr from a particle at the origin. And thus just 4 pi r squared dr, the volume of that shell, times the pair distribution function g of r by definition, right? Because g of r defines the number of particles per unit volume that are a distance r from the origin particle. So by definition, the number of particles between r and r plus dr is given by this expression in terms of gr. But we also know that if this is obeyed, then it's also given just by the derivative of this with respect to r, and so that gives you r to the d minus 1 with some constant in front of it. So we get a relationship between g of r and r to the d minus 1, and we can show that g of r, therefore, is some constant proportional to r to the d minus 3. Okay? So the pair distribution function for such an object, a fractal object, is a power of r where the fractal dimension enters this way. And so it can be written basically as 1 over r to the 3 minus d, since d is in general less than 3, so this is a negative power, and we write it this way. Now, the Fourier transform of a power law in R is a power law in Q. And so we see that S of Q and the Fourier transform in 3 dimensions of 1 over r to the 3 minus d is 1 over q to the d. So when you see a power law of scattering as a function of q, that exponent is often related to the fractal exponent. It can be determined directly from a small angle scattering experiment. So if you see that power law, often you can say that your object is a fractal with that dimension. And I'll give you examples of this shortly. So what the scattering formally looks like if you have a log I versus log q plot is you can have up to some length scale up to the size of the surface, length scale of the surface. You can get a power law which corresponds to what we call mass fractal, a volume fractal. And then when you really get to small length scales, you're sampling the surface, because the contrast is between the surface and air, or the solvent. And then you get, if the particle is rough, you may also get a surface fractal region. So you'll get another power law that takes over there. And of course, at very small q, you get the Guinier region. So this always saturates and bends over to becoming a constant here. So in general, these are the three regimes of small angle scattering: a Guinier regime, and maybe some power law regimes, and asymptotic power law due to the surface. And there's a theorem that is proved. I think I have some references for this later on, which shows that if you've got you can also have a surface fractal of surface fractal dimension d sub s, and the asymptotic form due to a surface fractal is not 1 over q to d, but 1 over q to the 6 minus d sub s. So you can see, for instance, if d sub s is 2, in other words, if this was a smooth surface, okay, where it's an integral number, and a smooth surface has a fractal dimension of 2, you get 1 over q to the 4th as the asymptotic scattering, and that's called Porous law, and is always there when you have a small angle scattering from random smooth surfaces. It's a special case of that. It's called Porous law. So consider these special cases. So in the asymptotic forms of the scattering, small angle scattering, suppose you have a bunch of randomly oriented cylinders. Then for Q, which are essentially where 1 over Q is greater than the radius of the cylinder, but is smaller than the total length of the cylinder. So you're in the regime where you're sampling the cylindrical part. S of Q goes like 1 over Q because the cylinder and those length scales has fractal dimension 1. A Gaussian random coil, as I've shown you, has fractal dimension 2, so S of Q asymptotically goes like 1 over Q squared. On the other hand, by the way, that's also true for thin random sheets, which are smooth sheets, which have fractal dimension 2 also. They also go like 1 over Q squared. On the other hand, a swollen polymer chain, which is not an ideal Gaussian coil, and is due to and can be modeled as a self-avoiding random walk, has a so-called Flory exponent, which is called nu, and its asymptotic form goes like 1 over q to the 1 over nu, and if nu is a half, then you go back to the perfectly random Gaussian coil, 1 over q squared. So all these forms, asymptotic forms, exist and have been analyzed. As you've got a bunch of randomly oriented smooth interfaces, that's Porous law, you get 1 over q to the 4. On the other hand, if you've got rough interfaces which look like surface fractals, it turns out that your q inverse power is 3 plus h, where h is the sort of self-affine fractal exponent of the surface. I think there's a question coming up here. Why are what fractals self-similar? A cylinder, if you have an infinitely long cylinder, then you can take a small part of that cylinder and still blow it up and it looks like the original one. Well, why these are fractal or self-similar? I'm not quite sure I understand the question. What are you asking about why are fractals self-similar? Well, that's sort of a definition of fractal objects. Why are these objects regarded as self-similar? Well, within certain length scales, even objects with integral dimensions can be regarded as fractal objects which are self-similar. I think I'm not sure whether I answered that question, but anyway, we're coming up for a break actually shortly. Well, almost, yes. So the question is, are almost all simple objects are fractal? Yes, but in a trivial sense. A solid object is a trivial fractal with fractal dimension 3. A smooth surface or a sheet of paper is a trivial fractal object with fractal dimension 2. And similarly, a long linear object is a fractal object with fractal dimension 1. But when the fractal dimension is an integer, then these objects we already know what they are, and we know how to characterize the scattering from them. But when they're non-integral, that's when you really have to characterize them as fractals. Okay, let's Let's go on. So here, for instance, is a small angle scattering from, this is actually X-ray scattering. That's why I call it SAS rather than SANS, because SANS and SACs are very similar. And this is an electron micrograph of a porous silica glass called Vycor glass, which is often studied for scientific experiments. It has a series of random pores, which are of the typical characteristic size of about 25 nanometers. And you can see here this sort of random pore structure in an electron micrograph picture. There's a detailed discussion of the structure of this glass in this paper here. And let me show you the scattering from this object. You see this sharp peak in the small angle scattering, and the solid curve is the calculated scattering from a digitized version of the electron micrograph. You can actually calculate the scattering from that in principle theoretically, and it agrees very well. And again, the position of this peak corresponds, is 2 pi over a length scale. That length scale is the pore size and is 25 nanometers for this glass. If you have other kinds of porous glasses, this will be shifted in Q. Now, an interesting thing about Vycor is that it's you can put things in it, like polymers and so on, and you can study the structure of polymers or other fluids in confinement, which is a very interesting problem in many ways. But of course, you've got the strong scattering from the Vycor glass. So the way you do it is to put the whole thing in a solution of H2O and D2O, which exactly contrast matches silica. And then you find that this, and you can easily see that because this peak rapidly decreases and eventually disappears. And all you're left with is a scattering from the polymers inside the pore. And so that's a very convenient thing you can do with contrast matching techniques with nuclei to make these kinds of the media or the things that you're putting the polymer or the thing you want, the protein or what you want to study in, you want to make them contrast match with the solvent and disappear so you can study the conformation of what you're putting in them. Pardon? Another question. Okay. Can we always assume that a power law slope is related to the object in solution? If S goes like Q to the minus 1 over a certain Q range, is it rod-like objects or can it be fortuitous or messed up by the structure factor? Well, of course, you could have a complicated structure factor for an object which looks like 1 over Q over a small range. But in general, if an object looks like some power law like 1 over Q over a sufficiently large range, then you can assume that it is actually got a large component which is linear, randomly oriented linear component to that structure. It's probably not fortuitous. But if it's over a tiny range, then I don't think it's significant. You have to consider the Q range over which these power laws exist. I mean, for instance, if something is fractal only between 1 nanometer and 1.1 nanometer, that's meaningless to say it's a fractal object, right? It has to be over a significant length scale, and therefore over a significant Q range. Okay, here's an example of a block copolymer electron micrograph, and you can see that phase separates in this lamella structure. When you cool it down, the two blocks like to phase separate from each other in this way, which is shown schematically here. And you can see scattering, small angle scattering from these lamella structures of block copolymers, and they give you a peak which corresponds basically to 2 pi over this interlamellar spacing, so you can determine that pretty easily. Also true for spinodal decomposition. Now here's another, all right, sorry, I'm missing your questions. What is a sufficient Q range? A decade? Yes, a decade would be good. Sometimes, you can cheat and even use slightly less than a decade, but I would say a decade is a good range to consider an object as a fractal over that range. Yes. Are there some other questions? In this, okay, so let me go back to that equation. So here, I think you're talking about this exponent h. So h is actually, we call this the roughness exponent. And it's actually related to basically the surface fractal dimension as well. So it's also 3 times the surface, 3 minus the surface fractal dimension. So if you've got a rough surface, you can also think of it as a surface fractal over some range with a fractal dimension, surface fractal dimension 3 minus the roughness exponent h. So that'll give you 1 over q to the 6 minus d surface, which is what I had before. But, you know, a self-affine rough surface, as I'll show you later on, is not the same thing as a self-similar fractal, which exists isotropically in all length scales. The self-affine fractal, which is the way a surface is rough, is usually different when you go normal to the surface and in plane. It scales differently. So that's why it's called self-affine rather than self-similar. Are there any other questions? Okay. Okay, now we're starting surface scattering. So this is a good time to take a little break. And so let's take a 5-minute break. And please ask me questions that you have about anything I've talked about. I'll try to answer them during the break, and then we can go on. Okay? Actually, Yitong, that this copolymer is fractal. I was just showing this as an example of another quasi-periodic phase-separated system, which is a lamellar system, which will give you a peak in the small angle scattering. I'm talking here about peaks in the small angle scattering rather than power laws in the small angle scattering. So fractals, self-similar objects, give you power laws. Quasi-periodic structures like this, or the pore structure you find in Vycor that I showed, give you peaks. And that peak is related to the periodicity as 2 pi over the periodicity. So that's all I was trying to illustrate here, not that this is a fractal object. I don't mean to imply that. So the higher the dimension, the faster the scattering drops. Well, that's a good question. I'm not sure I know how to answer that. It's certainly true the power law drops faster with a higher value of d, and I think it just says that if an object is a high fractal dimension, it's more compact, so it has more length scale concentrated at shorter distances. Thank you. So I really think it's just related to this property. I'm not sure I'm able to give you a good qualitative answer, but it's just related to the property that the Fourier transform, if an object has a large d, then basically its g of r function drops more slowly with r. So a large d means the object is more spread out as far as its distribution function is concerned, and so in reciprocal space the scattering drops. Whereas a tenuous object, drops more rapidly as you go out in space, in real space, and so it hangs in more as you go out in Q space. It maintains itself because they have an inverse relationship to each other, these power laws. There are, by the way, many such images they all look very similar. Lamellar phase separation of block copolymers, spinodal decomposition of 2 kinds of fluids or metals, and magnetic domains forming in ferromagnets, for instance, striped structure of domains. They all look like this worm-like random but quasi-periodic structure. All right, I think maybe we should go on because we only actually have formally another 10 minutes or so. So let me just start the bit on surface scattering, and we'll have to finish up next time. So I'm now going to talk about, we're done with small angle scattering. I'm going to talk about surface or interface scattering. Here's a list of things you can study with surface and interface scattering. I'm sure there are many more applications. I've just listed some of them: wetting films, film growth exponents, capillary waves, fluctuations on liquid surfaces, or complex fluids, polymers, microemulsions, liquid metals even. islands on block copolymer films, pitting and corrosion on surfaces. Magnetism, you can study magnetic roughness, the morphology of magnetic domains in magnetic films. You can study nanodot arrays, adhesion, electrodeposition, tribology, and so on. So it has many applications. And so let's talk about reflectivity. So here is what you're very familiar with, a reflection in a mirror, and this is typically called specular reflection. This is in the case of visible light. So if you've got a smooth surface like the water here, the reflection is essentially specular, as you can see. It acts like a mirror. On the other hand, if you've got a disturbed surface of the water, then you can see that you get, of course, some component which is specular, but you also get a large diffuse component, and that is due to the fluctuations on the surface of the on the surface. Yes. Actually, the scattering from the fluctuations is actually coherent, but so it's not random. I mean, so it's not statistically random in the sense that there's some actual structure to that. Like no more than a fractal is statistically random, but it has a kind of a coherence to it that gives you a power law. So it's not the same. A totally incoherent neutron scattering would give you a completely featureless Q-independent scattering, okay? Whereas diffuse scattering from a rough surface certainly has important Q dependence that you can analyze to get some information about the roughness. So the question was whether you could think about specular and diffuse scattering as the analogs of coherent and incoherent. To some extent, that's true, actually, but in some other sense, it's not the exact analog of incoherent neutron scattering because that really is featureless in Q. Whereas diffuse scattering does have a Q dependence, and that's important. So specular reflectivity measures the variations in the scattering density normal to the surface, averaged over the xy plane, whereas off-specular scattering measures the in-plane variations of the scattering density due to roughness, or in the case of magnetic films, magnetic domains, and so on. Now here's the typical diagram for surface scattering. So here is the physical surface. Here is the incident wave vector making an angle alpha sub I, which is called the grazing angle of incidence. It's typically 90 degrees minus what's known in optics as the angle of incidence, which is the angle with the normal. This is the angle with the surface. It's called alpha sub I, the incident grazing angle of incidence. And the outgoing angle is alpha sub F, which is the outgoing grazing angle of scattering. And you can see that this is the outgoing wave vector, incoming wave vector. This is the wave vector transfer Q. If this is if these angles are the same, then you get specular reflectivity. The angle, incident angle equals the outgoing angle, and then Q is actually normal to the surface, and we call this the specular rod, the specular ridge. All the scattering along this ridge in Q space normal to the surface is specular. Of course, you can arrange for your scattering wave vector by tilting your sample or moving the detector. You can arrange for the scattering vector to be off that normal, in which case you're sampling off specular scattering or diffuse scattering, and that measures the in-plane fluctuations. So specular reflectivity corresponds to the Qx and Qy components defined in the plane as being 0, and only a Qz component, which is given by 4 pi over lambda times sine of theta, where theta here is the same as the angle of incidence alpha. Now, the basic equations for reflectivity are given by the well-known Fresnel theory. We assume that the medium, because this is basically small angle scattering, so we can assume the medium is a smeared out medium and not a collection of atoms, and therefore can be described by refractive index, which has a real and an imaginary part, which represents absorption, and this represents the dispersion part of the refractive index. And the Fresnel theory says that if you've got a medium of refractive index n and refractive index 1, which is free space, you've got a beam coming in and a specularly reflected beam going. If this surface is smooth and is completely sharp and featureless but smooth, then you've got just simply a reflected beam and a transmitted beam, and the conditions are that the in-plane component of the wave vector is conserved. So the k outgoing wave vector projected on the plane is the same as k incoming projected on the plane, and the normal one is related by the fact that the total wave number inside the medium has to be n times the wave number in free space. And given those two conditions, you can work out the Snell's law of refraction and the theory of reflectivity. Now, the Helmholtz equation and the boundary conditions which I just described, that the wave coming at the surface, the electric field has to be continuous at the surface and continuous along the surface, which gives you the conservation of k parallel to the surface. The equation that has to be obeyed subject to those boundary conditions is the Helmholtz wave equation, which is given by this. This is either the electric field of an X-ray, where the electric field is assumed here to have S polarization parallel to the surface, or in the case of neutrons, this is the neutron wave function, which is a scalar. And inside the medium, you can have effective refractive index, which is k times n, and we are giving n an r dependence because we're assuming that this medium is not completely uniform, but it has some positional dependence. We're averaging over the x and y part, and we're assuming only some depth dependence to this refractive index. As you will see, this will give us the Fourier. This will give us the nuclear density profile normal to the surface. So anyway, this is the equation we have to solve subject to this boundary condition. So let's assume n is first of all constant, and when we do that, first of all, how do we define a refractive index? For X-rays, it's just the same as in optics, but in the case of neutrons, you have to consider the Schrodinger equation. By the way, this symbol here is meant to be h bar. It didn't translate properly in Adobe PowerPoint, but whenever you see this little box, it means h bar. So here's the Schrodinger equation, and this is the potential that the neutron sees in the solid. This is the neutron energy. This is the neutron wave function. And the energy, of course, is h bar squared over 2m times the wave number in the incident space that it's coming in at. That's the total kinetic energy of the neutron. Now, this equation can be recast in this form. So this is rewriting the Schrodinger equation to look like the Helmholtz equation. Now, this V now is the average potential the neutron sees in the solid. Now, as we will see, the potential between a neutron and an individual nucleus is given by this thing 2 pi squared over 2 pi h bar squared over the mass of the neutron times the scattering length times the delta function. This definition with these prefactors gives you, in the Born approximation, the scattering which looks like a spherical wave with amplitude b. Okay, it turns out that that's why you have to put these factors in. And so the average potential, if you average this over the density of nuclei, you'll find that 2m over h bar squared times the average potential, which is this part of this expression here, is simply 4 pi times the nuclear scattering length, coherent nuclear scattering length, times the density of nuclei per unit volume. And so, and if, of course, you get different types of nuclei, different types of atoms, you have to weight them by their respective densities and scattering lengths and get the average scattering length density. So this is the scattering length density. If you compare this equation with the Helmholtz equation, which is this, you can immediately see that n squared for neutrons is given by this expression. If you substitute for V, you substitute this expression here. And you can see, therefore, that since this is a small quantity of order 10 to the minus 6, you can take the square root of this and expand it, and you find that n, to a good approximation, is given by 1 minus something which is proportional to the square of the wavelength, the nuclear scattering length density, divided by 2 pi. And so that's what sets up the refractive index. And our time is up, so I will just say that next time we'll discuss how reflectivity and diffuse scattering arises from the solution of this Helmholtz equation and the boundary conditions. And we'll talk about that next time. I know the time is officially up, but I'm happy to answer. For those of you who want to stay, I'm happy to answer any questions you might have. Okay, so if not, anyway, for the rest of you, thank you very much for your attention, and I will see you next Tuesday where we do lecture 3. Anybody else? Anybody here in this room have a question? Anybody in the audience have a question? There's no absorption. So in discussing the refractive index, there's a small imaginary component which gives you the absorption. And when you consider the rigorous theory of reflectivity, of Fresnel reflectivity, you actually have to put that imaginary component in n, because then it takes into account the absorption rigorously. So the question was, what about the absorption? And the answer is, you take that into account by putting in the full complex refractive index when we discuss the expression for reflectivity in terms of refractive index. But the real part, which is delta, I'm sorry, the real part which is delta here, is related to the electron density, actually, to the nuclear density in this case, scattering length density. So it gives you the density profile, and this imaginary part simply gives you some corrections to it due to absorption. We'll see how that works out. Yes. Yes, I should point that out. One of my students in this room has pointed out that if you go to the NIST website, cold neutron facility, research facility, they have, you can access a place where they calculate neutron scattering length densities of various kinds of materials. So that can be very useful, especially if you want to estimate how much contrast you have for a small angle experiment, for instance. Thank you for pointing that out. I think I have a list of references which I'll go straight to at the end of this. So it'll be in the next set of notes on reflectivity, small angle scattering, and so on. I have these references for further reading, and they will be in your notes. Okay, thank you very much. I think